it's Larson in the lab with Chemistry Cook today. Welcome. Now, we've been talking about electron configuration, and we are going to do a lab that is actually probably one of the more fun labs you'll do all year. And you might be thinking, how is 1s2, 2s2, 2p6 going to be fun? Well, let's explain. Ms. Cook, take it away.
Well, we've been talking about electrons in the ground state, meaning the lowest energy level possible when we write electron configuration. But are electrons always going to be in the ground state? The answer is no. We can actually make the electron leave its irregular electron configuration position, the ground state, gain energy, and go to a higher energy level. So let's talk about how we're going to do that. So we're going to look at Bohr's model of the atom. That's just the original kind of model of the atom, the planetary model that you've been studying throughout your years of science. So I'm going to draw an electron in Bohr's model. So we're going to represent the electron here. That lowest energy position in electron configuration is called the ground state. So the electron's going to start in the ground state, and we are going to add energy to it. We can add energy to it using a flame, which we're going to do today, or you can use electricity. So let's pretend that we're going to add energy to this electron. So we're going to add energy to the electron, and it's going to literally jump into a higher energy position. So the reason it was able to do that is because it absorbed all the energy from the flame or electricity that you added. This higher energy position is called the excited state. Just like if you get super excited about something, like something you got for Christmas, a new car, the electron is in an excited state. It's got a lot of extra energy. But you can't hold on to that energy forever. So what's going to happen is the electron is going to lose that energy, and it's going to fall back into the ground state. So when it falls back into the ground state, all that extra energy is released in the form of light. So I'm going to use my yellow marker to show all the light being given off. So how do we know that that light comes from that electron? Well, if you'll remember back from physical science, light is a wavelength. So we've got a wavelength of light that's coming off of that electron transition from the excited to the ground state. And remember, wavelengths correspond to Roy G. Biv. And so we're going to see today that several elements are going to make this transition with the electrons from the ground state to the excited state, falling back to the ground state, releasing the extra energy as a wavelength. Each element, because their electron configuration is unique just for them. Like, for example, hydrogen is 1s1. It's the only element that's 1s1. Helium is 1s2. It's the only element that's 1s2. Because each element has a unique electron configuration, this falling back is going to release a unique wavelength of light. So all elements are going to make a different color. Now, some of them might look similar, so we might need some additional instrumentation, like a prism or a spectroscope, like you might have used in an earth science class, to see the different wavelengths that are given. All right, Ms. Larson.
All right.
Are you ready?
So what we're going to do is, as we test each of these different elements, we are going to record what color flame comes from that wavelength, or which wavelength of light comes from that element as the electron dumps back down to the ground state. So we are going to start with barium. It's all the way over here, and we are going to add energy by adding a flame, a heat and light energy to it. And we are going to see what happens as those barium electrons get excited and then jump back down to their ground state and release light energy.
And that's why we have the lights off, so you can see that.
All right. So it's going to take a moment for the alcohol. We have alcohol here and then a barium salt. And we're going to be able to start to see what color barium gives off as it continues to burn and get to the barium salt.
We're waiting. It's going to be great.
Sometimes
it's going to be great.
Science doesn't always work as fast as you'd like it to.
But we get to watch the alcohol burn in the meantime.
And also, we're both wearing our goggles. That's part of a big lab safety issue for us. If you're using heat or flame or chemicals, you must wear your goggles because you don't want to damage your vision. We're also wearing masks because we're within 6 feet of each other and coronavirus. All right, it looks like it's burning down to the salt very, very soon. Let's give it a moment. Science doesn't always cooperate with our timelines.
We should have brought marshmallows, Miss Larson.
We could have.
We could have brought marshmallows.
It would have been pretty fun. Come on, barium. It's starting to get there, guys. Thank you for your patience. What are we gonna do, barium? Oh, it's starting to go. Let's see. Come on, barium. Okay, did you see it?
Okay,
it's a really small flash.
It's a really small flash of green.
It was a greenish flash in our barium.
Oh, I saw it.
There it is. Look at it.
That was not the best element to start with.
That's okay.
That's okay.
Science doesn't always work how you want it to.
I think we're going to use Mr. Gauck's blowtorch.
Yes, we might. But hey, barium produced a slightly green flame that you could see. And also, by the way, I'm going to ask you to look up the symbols for these different elements. And note that barium had a green flame, even though it wasn't a super strong flame. Oh, no, by the way, we're doing this way because we don't have gas in our chemistry lab this year due to construction, and so we can't do this with a Bunsen burner.
Which would have been faster.
But hey, we make do with what we have. Here comes copper, guys. Another way we could do this is if we had a bonfire, we could have put some of these copper salts or barium salts on there and see what happened. Ooh, do you see it?
It's a little green.
A little greenish, kind of teal green color.
I think the Irish would enjoy this for St. Patrick's Day.
This would be a great use of barium to create a St. Patrick's Day themed flame.
Yes. Now, one of the interesting things is if you ever see a firework, and it has a green color in it, the firework has copper in it. So this is the same principle that we use when we make fireworks. These electrons in copper are going from the ground state to the excited state, and then as they fall back to this ground state, they're releasing that extra energy as a wavelength, and our retina is picking that up as green.
Yeah. So I'm gonna put greenish, like dark green, kind of teal here. Teal, green color. So if your favorite fireworks are like these ones, this little tealish color, you are looking at copper going back down to its ground state.
All right,
we're gonna let that continue to burn, but we're going to go ahead with lithium. Lithium. Ooh, do you see it?
I think I see some red.
Red, kind of like a pink red color.
Yes.
Very red. That one is looking very, very good. That one, these two have been working a lot better than the barium.
I think the barium was disappointing, but this is better.
A bit disappointing.
But you can even see the copper is getting a little bit more prominent in its green color, but the lithium is very nice red.
I'm going to put down red, and you'll put that in your data chart as well. Okay, next up, let's check out strontium. We had a little bit extra alcohol on the strontium, so we're going to pour it off and see what happens. Ooh. That looked pretty nice.
That was pretty nice.
Kind of like an orange red.
I would say an orange red.
Orange red color. So if you like fireworks that are green or pink, pinkish red, or an orangish color, then you are looking at copper, lithium, or strontium and enjoying that. That looks really nice.
Yeah, the strontium has this nice, really deep orange.
Deep orange. I think that's a great description.
Well, thank you.
All right, next up, guys, is Potassium,
All right.
which, by the way, is chemical symbol K, not P. P is for phosphorus. We're using our Latin words here.
So this one, it's kind of hard to tell on the video, but it's making like a purpley, pinky, peachy color. It's very faint, but compared to the strontium, which is a really bright orange flame, you can see that it has a little bit of a lavender touch to it, a little bit of a pink. It's very, very faint. So if we're doing this in person in a non-pandemic year, we would be able to see that pinky purpley color a little bit more prominently, but it's very, very faint.
Good. Yeah, and I can see the purple. So I'm going to go ahead and add purple,
I would say purple
to our data table. All right. I think you would see it more as well if we were able to use our Bunsen burner.
Oh, the Bunsen burner is the best.
Hot flame. The hotter the flame, the more of those electrons would jump up in energy level and then fall back down. So,
and you can actually tell as it burns a little bit more, we're still starting to see some of that purpley color. So you can keep your eye on that while we also light the next element, which is
calcium.
All right.
Ooh, here comes that kind of orange.
Oh, that's like an orangish red.
Orangish red.
I would say an orangish red. You can see a little bit. Now, as it burns off the alcohol, you're going to see that orangish red become a little bit more prominent as it burns more of the calcium salts that we dissolved in the alcohol.
But you can start to really see it flicker at that orange red. I think we'll get a stronger reaction as the alcohol
We're going to need to wait like we did for the barium one on this one.
And it's starting to show up a little bit more. So you can see little flickers of that dark orange red color. So I'm going to go ahead and add dark orange red to our data table. All right, and last but not least, we're working with sodium. So let's see what sodium will do.
I broke the match.
Uh-oh.
Try again. Now that is making, I think, Miss Larson, an orangish, yellowish flame.
Yeah, like a bright orange yellow.
I would say bright orange yellow.
That's kind of different than that orange that we saw with the calcium. The orange we saw with the calcium was more of like a dark reddish orange, but this is more of a bright yellowish orange, and it's a pretty strong color show here.
And the interesting thing about the flame test is if we had another instrument like a spectroscope or a prism, we'd be even able to see the different wavelengths that make up that orange color. But I think bright yellow, orange,
or bright orange yellow.
Yes, I think that's a good conclusion.
All right. So now what we're going to do is we're going to let you see what you know about these different elements based on which colors, wavelengths they're giving off as their electrons move from that excited state back down to the ground state. We have 3 unknown elements, and you're going to use your knowledge from what you've just seen in this flame test to identify those unknown substances. And this is a way that possibly early chemists could have identified some of their different elements that they had found by doing a flame test before they had more advanced technologies.
All right, so we're going to try unknown A. That means it's going to be a repeat of one of these elements that we've done in the past. So we need to match our observations from unknown A to one of the ones that we've done recently and see which one it matches best.
That's an interesting flame.
That is very interesting.
It hasn't really started to pick up much color yet.
Not yet. We're going to wait for it to burn. Now, there was another one that we had to wait for it for quite a while
Right.
to burn before we got to see a color.
There was one. Could this be that one?
It might.
It might be. What is unknown A?
Oh, did you see it? It was a light green.
Little flash of
a
green.
little flash of green. I saw it.
Oh, there it was again.
I saw, yep, a little light green.
Like a
color.
lime green.
Lime.
Oh, there it is.
That
Wow.
was nice. This is really good.
This is a really good one. Okay, I'm going to put bright green.
I think you should
in the
put
data
bright
table.
green.
And then you guys have the job of determining which element would have made a bright green a reaction or flame, and determine what was unknown A based on that bright green color you saw. All right, next up, our second unknown. It's unknown B. And you're going to try to find out what is this? What element is this? Ooh, that's really pretty right from the start. Are you seeing purple?
I'm seeing a little bit of purple. A little like...
At the bottom of the flame,
yes,
you can
at the
especially
very
see it.
bottom, right where the salts are. So kind of like, I would say like a light purple.
Light purple?
Yeah, I see it.
One of ours that we had before was definitely light purple.
Yeah, right at the base of the flame.
Mm-hmm.
That's pretty.
That is pretty. I think if I were going to make a firework, I would make it with unknown B.
I would definitely use unknown B.
Kind of a white purple there. All right, guys, we've got one more for you. It's unknown C, and we're going to see if we can find out what it is.
That was a good pun, Miss Anderson.
And it's, you know,
I like it.
a little bit cheesy sometimes.
That's okay.
What are you seeing? I'm seeing some red.
I'm seeing some red. That's a pretty deep red, too.
I think so. If I were an Alabama fan.
Oh, now this one.
And I were making Alabama-themed fireworks, or even Ohio State.
This would be the one to use. So in my firework, I would want to use unknown C.
You would want to use unknown C? Like a deepish red.
Deepish red, yes.
Deep red.
Deep red. Okay.
All right.